Welcome to section 13.3. We are going to evaluate trig functions of any angle, and the difference in this section is it's not just going to be used in terms of the unit circle, it's going to be any coordinate point on a graph. And so here's what we're doing. We're giving you a circle, again, not a unit circle, but just a circle, and we're looking at a point that's on that circle, and that point's xy. And what I want to do is start by drawing a right triangle. And anytime we give you a point, we want you to draw this right triangle in so that you look at it and you say, okay, here's my triangle. Okay, now as I look at this triangle, to get to the point xy, I move to the left a value of x and up a value of y. And then the length of the hypotenuse we call r, which is part of the radius of the circle. Okay, your angle, because the sine is positive in quadrants 1 and 2, the sine value will always be the same. So if I call this a big angle theta, what I can actually do is call this inner angle theta as well, and it won't change the sine value, cosine value, anything like that. So take a look. Okay, so let's try and write our sine. If my angle is right here in the inner part of my triangle, then the sine is opposite over hypotenuse, so it's y over r. Now here's the big thing, r can't be negative, right? The radius of a circle will never be 0 or never be negative, or you don't have a circle. So that's kind of the idea. Take a look, the cosine is the adjacent over the hypotenuse, so it's x over r. The tangent is opposite over adjacent, so y over x. And again, we don't want the value of x to be 0 or we have an undefined fraction. So that's going to be one of our stipulations. Cosecant flips, so you take r over y. Again, we don't want the value of y to be 0 or we don't have a fraction. Secant is r over x, same stipulation. Cotangent is x over y, same stipulation. All we're saying with these ones basically is we just want to actually have ratios, so we don't want them to be 0. These are called circular functions because, again, you can put them on the circle anywhere on the coordinate plane. Now, we're not going to use a circle very often in this section. Excuse me. Here's what we're going to say. Let me give you a point, negative 12, 5. And what I'm going to do is plot that point, and then what I'm going to do is draw my triangle. So I have this length, and I have this length, and then I have my hypotenuse, right? The hypotenuse is what we always call r, but now let's label my sides. To get to the point negative 12, 5, I go left, negative 12, and then I go up, positive 5. Okay? Now, it's okay that a side length is negative. You can't have the hypotenuse be negative, though. And let me show you why. If I go to find the hypotenuse, I have 5 squared plus negative 12 squared is going to equal our r squared. 5 squared is 25. Negative 12 squared is positive 144, because when you square a negative, you get a positive. This ends up being 169 equals r squared. So when I square root 169, the radius ends up being 13. And that's something you should kind of know is a special right triangle, a 5, 12, 13. So kind of keep in mind, if you don't, those are some things you want to think of. 3, 4, 5, 5, 12, 13. There are other ones out there, but that's one. Excuse me, that's one you're going to see more often. Okay, take a look. Let's write our ratio, because again, the angle can be put right in the inside too without affecting the ratios. So if my angle's right inside by the origin, your angle will always be right by your origin. Keep that in mind. Then my sine is opposite over hypotenuse, so 5 over 13. Cosine is adjacent over hypotenuse, so negative 12 over 13. Tangent is opposite over adjacent. It's 5 over negative 12, but I'm always going to put my negative on top. Doesn't quite matter. Cosecant flips the sine, so 13 over 5. Secant flips a cosine, so negative 13 over 12. Again, I always put mine on top. It doesn't mean the 13 is negative, it just means one of them is negative. Cotangent flips a tangent, so negative 12 over 5. Okay, so you plot a point on the coordinate plane, and then you label its sides, find the hypotenuse, and go. Overall, it's hopefully pretty nice. Let's keep moving. A unit circle is centered at 0 with radius of 1, and we have been talking about this unit circle forever, and we're going to continue to talk about the whole try. A quadrantal angle, that's a word you need to know. A quadrantal angle is an angle in standard position whose terminal side lies on the x-axis. So you're talking about values like this. You're talking about the angle being 90 degrees because it'll end here. You're talking about the angle being 180 degrees because it'll end there. You're talking about the angle being 270 degrees, it'll lie down there, and you're talking about the angle being 360. Now I could keep going. I mean, this could be 450. It could keep, I mean, I could keep going the whole way through. I could end up in saying 720. The idea is any quadrantal angle, basically you end on the terminal side. Well, the hypotenuse of a unit circle is the radius, right? So the hypotenuse, if you kind of think of a triangle, and this is a hard idea to look at a triangle with no height or base or whatever you're looking at. The idea is the hypotenuse is 1. So when I do this, and let's say I'm going the cosine, this is how they determine the cosine stuff. The cosine is your adjacent over your hypotenuse, and adjacent is always x. So your cosine is x over the hypotenuse, which is 1, or just x, which we know that because we said every point xy equals the cosine of an angle, and every y value was the sine of the angle. That's what we talked about in the first day of unit circles. So the sine is the y value over 1, or just the y. And so this is where this whole idea came from. As I'm looking here, is I can start talking about them in terms of angles. And that's the only idea. This idea, you just need to know when they say a quadrantal angle that you know it lies on one of the axes. Okay? So let's flip to the back side. Alright, take a look at this one. We have 3 pi over 2 as our angle. Now, if I convert 3 pi over 2 to a degree, I end up getting 270 degrees. Now, you can just use your unit circle for this one. So what it says is I start here, and I end at 270 degrees. There's my angle. Okay, so let's actually use our unit circle at this point in time because I think it's the easiest. The sine of 270 degrees is -1. Okay, the cosine of 270 degrees is 0. The tangent is sine over cosine, so it's -1 divided by 0, if I write this, which is undefined. Okay, cosecant is the reciprocal of a sine, so it's 1 over whatever your sine value is, which is -1. Your secant is the reciprocal of a cosine, so 1 over my cosine, which is undefined. And your cotangent is now cosine over sine because it's the reciprocal. So I'm going to change it this way. Cosine is 0 over sine is -1. 0 over -1 is 0. Okay, again, keep in mind, you've got to know that tangent is sine over cosine to be able to do a lot of this stuff. Okay, and again, most of this comes back to the unit circle. I mean, I can relate everything we do in here to the unit circle, and you should be doing that as well. Let's take a look at reference angles. All right, there's this idea of a reference angle, which means I can find an angle in any quadrant with the same characteristics as an angle in the first quadrant. Okay, so we call this thing theta prime, and theta prime just as a theta with like a apostrophe. That means our reference angle. Okay, now a reference angle has the same terminal side, and the goal is to get to the x-axis the quickest. Okay, so get to the x-axis quickly. That means some of the time you will go backwards, some of the time you will go forward. One thing to keep in mind though, reference angles are always positive. Okay, keep in mind, I will mark them wrong if they're negative. Okay, so take a look. If I give you an angle, theta, it's in the second quadrant. The question is, what is this extra, and how do I find it? Well, because I'm getting to this negative x-axis is the quicker way instead of going backwards, what I'm going to do is this positive x-axis is 180. So I'm going to take 180 minus the original angle, and that's going to get me my reference angle. In terms of radians, 180 is the same thing as pi, so we take pi minus our angle. If my angle is greater than 180, the question is it quicker to go back to the negative x-axis, or is it quicker to go all the way over to the positive x-axis? And the answer is to go to the negative. So the question is, what's this overage that I have? Now remember, reference angles can't be negative. So I'm looking for the overage. And the way I'm going to do that is I'm going to take my original theta and I'm going to subtract the 180, and that will give me this extra piece. In terms of radians, it's my theta minus pi. All right. If I need to go, if my angle is in quadrant 4, the question is it quicker to go to the positive x-axis or quicker to go back to the negative x-axis? And the answer is quicker to go positive. And so how do I find this leftover piece? I'm going to take 360 because it's closer to get to 360. And I'm going to subtract my angle. Now, in radians, 360 is the same thing as 2 pi, so I do 2 pi minus my angle. Now, most of the time when you do reference angles, it's so much easier to draw a picture. And so that's what we're going to do. Take a look at the at 3. Let's start with A, and I'm going to see if I can move this up a little bit so we have some room. If I look at negative 165, I'm just going to draw a picture here for a second. I always start at my positive x-axis. Negative 165, I go back 90 and then an extra 75, so that's like right here. So here's negative 165. Now my question is it quicker to go to 180 or is it quicker to go back to 360? And I think you should look at your picture and see that we can go to 180. Now that's my reference angle and theta prime. Sorry about that. I'm not sure what's happening with my iPad. Okay. So the question is, how do I find that overage? Well, what I'm going to do is, because it's kind of the same thing as if I went in this positive direction. I'm going to try and not kill this picture. It's the same thing as if I went like this. My angle would still be the same. I'm going to take 180 and subtract the 165, and that'll kind of tell me this leftover piece. And what we end up finding is it's 15 degrees. So theta prime is 15 degrees. Now, if they give you an angle in a radian, we expect that your reference angle will be a radian as well. So I don't know what 7 pi over 12 is, but if I converted 7 pi over 12 and I multiplied it by 180 over pi to convert, what you would find is that it's 105 degrees. And so if I draw a picture, okay, and I'm looking at this, 105 is not that far. Let me get rid of this piece. 105 is like here. So here's my 105. Okay? Is it quicker to go to the negative x-axis, or is it quicker to go backwards? I think you'll find the positive. So in order to do that, we take 180 minus 105, and you get 75 degrees. Now, here's the problem. They gave me my answer, or my original question was in radians, so your answer has to be in radians. So you have to take 75 degrees and multiply by pi over 180 again to get yourself back. What you end up getting is 5 pi over 12, and so this is my reference angle. Okay, and for most of us, we're going to have to convert our way through this because we're not comfortable with radians. Okay, last one. 322 is my angle. 322 is in the fourth quadrant because it's between 270 and 360. And so it's like right here. Okay, if this is 322, is it quicker to go up to 360 or back to 180? I think you'll see it's quicker to go up to 360. So we take 360 minus 322, and you end up getting 38 degrees. So my reference angle is 38 degrees. And again, we're going to be using reference angles kind of the whole way through. So just kind of be aware of that as we go. They will ask you for reference angles. One more page, let's kind of flip that. Okay, we can use this idea of reference angles to help us evaluate a trig function. And here's what I mean. I'm asking you for the sine of a negative angle. Well, let's look at negative 225. Negative 225, well, here's negative 90, negative 180, negative 225 is halfway through. Well, instead of saying negative 225, what I can do is look at the positive version. Instead of here and starting this way, it's the same thing as the sine of 135 degrees. And it's kind of that idea of coterminal angles that we've kind of talked about before, but it's that idea as we look at this. Well, I can easily find the sine of 135 using my unit circle. And if you do that, sine is a y value. Y is positive in quadrant 2, so it's positive square root of 2 over 2. And that's kind of the idea going through. Second one, cotangent 5 pi over 3. Well, cotangent of 5 pi over 3, I don't know that angle, but I can look at my unit circle, and what I find that 5 pi over 3 is the same thing as 300 degrees. Well, cotangent, if you look at 300 degrees, okay, that's down here. It's the same thing as this 60-degree angle in the positive, only something's negative down here. And what's negative down here is the sine value is going to be our negative, because cosine is positive. So here's what I want you to do. It's really the same thing as saying the cotangent of negative 60 degrees, or 60 degrees where you make sure the sine is negative. And as I do it this way, here's what I'm looking at then. The cosine of negative 60 divided by the sine of negative 60. And the sine value is going to be negative. So what you get is 1/2 divided by negative square root of 3 over 2. And again, the 2's will cancel out because they're both in denominators. So you have 1 over negative square root of 3, and we have to rationalize. You end up getting square root of 3 over negative 3. You can leave it like that, or I can normally put my negative on top, but that's kind of the idea. I'm going to save these extra ones because they're not specifically in your book, so I'm going to save those for class just kind of as we're going through. But I do want to talk about this next piece because this next piece will kind of help you with some hints kind of along the way. We use this in pre-calculus a lot, but here's the idea. There is an acronym to help you figure out which trig values are positive and negative and in which quadrants. And then what we use is all students take calculus. And let me show you what this means. All means sine, cosine, tangent are positive, so are then their reciprocals. In the students column in quadrant 2, what it means is sine is positive, and you can kind of see that sine and its reciprocal, the rest are negative. In quadrant 3, this means t means tangent is positive, and you can see that and its reciprocal, the rest are negative. Calculus means cosine is positive. You can see cosine is and its reciprocal are positive, and the other two are negative. And so the acronym we use is all students take calculus, and that's our way of kind of helping figure out which ones are positive and which ones are negative. Just kind of something to try and help you with. I have one application, then I just want to briefly talk about the extra credit. The application talks about ships, and so you have this ship, and pardon my drawings, but here's this idea. You have this ship that sails 512 miles on a bearing of 12 degrees. What that means is as they start traveling north, let's say, they end up shifting off course based on like wind speed and things like that. They end up shifting off course a certain degree. And so that ends up being, in this case, 12 degrees. And what it tells you is they actually did travel 512 miles. And so the question is, as we go through and we ask them, once, they go 512 degrees, or 512 miles, how far east, how far off course are they from the original position, which we call X? as I look at this, I know I have a 12 degrees, and this is my opposite, and this is my hypotenuse. So we know that the sine of 12 degrees is going to be my opposite over hypotenuse. So I'm going to multiply by 512, and I end up finding that I get off course about 106 miles. And the reason I say 106 is they ask you to round to the nearest. But I wanted you to know this idea of a bearing because this is something that you could see quiz test-wise as we're going through. The last one is a story problem, and this story problem is going to be extra credit. I will put 5 points towards your test, and that's huge. That's 5% on your test. You may use this in groups if you want, and put all of your group names on one paper is perfectly fine, but you're talking about a Ferris wheel. And again, your Ferris wheel, and you need the diameter of a circle, and all of that kind of comes into play. And drawing the picture is huge. And so if you have questions about drawing the picture, we can talk about them in class, but this is extra credit, and it is towards your test. So that's the end of section 13.3. Don't forget, again, unit circle. You'll need to be studying unit circle for the quiz, and also we have a quiz 13.1 to 13.3 coming up. So thanks for watching.